Hello students, myself Dr. Subarna Dotto. Today I will start module 4, that is electronic materials and semiconductor physics. This is the syllabus of module 4. Before starting the module 4, I will discuss what is the importance of electronic materials. So there are different types of materials in nature, that are semiconductors, insulators, conductors, organic polymers, composite materials, and many more. These are some of the examples of semiconductor, insulator, conductors, and so on. Now, what is the overview of engineering materials? That is, there are several kinds of materials, that are metals, polymers, ceramics, composites. All of you know that the metals have metallic bonding, semiconductors have covalent bonding, polymers have covalent and secondary bonding, and so on. And all of the materials have some advantages and disadvantages too. So if you can combine with some metal with ceramics, then the output product will be very much different from the metals and the ceramic parent compound. So material scientists can combine any of the material in the laboratory, and they can make various material which have extraordinary properties which are different from their parent materials. Now, what is the importance of material science? So, material science teaches us what the things are made of and why they behave so. That means why the materials have some types of properties. And material engineering shows us how to apply the knowledge to make the better things and to make things better. That means to make any material which has better performance. Material science drives innovation in both research and industry purpose, and it focuses the most important characteristics of materials such as electrical, thermal, optical, magnetic properties, and so on. And in the material science, the material scientist or the physicist, they can combine the mechanical, chemical, magnetic, optical, or thermal properties of any compounds to make other properties, and it gives, we can apply this type of materials in the devices and make improved device. Now, what is the importance of nanotechnology? So, what is nanotechnology? Nanotechnology is manipulating materials on an atomic or molecular level. So, here we have given one example, that is graphite. So, all of you know that graphite is an allotrope of carbon. It has a high number of carbon sheets, whereas in its 2D form, that is graphene, it is a single carbon sheet of graphite. So graphite is a non-metal, but it has electrical conductance. It can be used in pencil, in lubricants, in anode batteries, and so on. But the graphite is ductile in nature, whereas in its 2D form, in graphene, it is the 200 times tougher than steel. So it is a very rigid, tough material, and its electrical conductivity is very high. Now, if you can roll the graphene sheet, then it will be carbon nanotube. It is a tube-like structure, and depending on the direction of the rolling of carbon nanotube, it exhibits metallic or semiconductor behavior, and the semiconductor, it has tunable band gap. That is why it can be applied in any electronic devices. Now we will go to its zero-dimensional form, that is the quantum dot-like structure. This is fluorine C60 molecule that consists only 60 carbon atoms, and it looks like a soccer ball. And the C60 compound, the fluorine, exhibits or behaves like a complete insulator. So one material, carbon, when it goes to its 3D to 0D form, its electrical conductivity is drastically changed. So that is the importance of the nanotechnology. Now I will come to your syllabus, that is the free electron theory. So all the materials, its fundamental element is atom, and in atom the fundamental particle is electron. Okay, so if any material shows good thermal conductivity or electrical conductivity, that is due to the free electrons. And insulators, it has no such free electron, that is why they are bad thermal conductor and electrical conductor. Whereas in the metals there are lots of free electrons, that is why it has good electrical conductivity and thermal conductivity also. So in solids, electrons in outermost orbits of atoms determine its electronic properties, electrical properties, and the electron theory is applicable to all the solids, both metals and non-metals, and it can explain the electrical, thermal and magnetic properties of solids. So the structure and the properties of solids are explained employing their electronic structure by the free electron theory of solids. So there are three main free electron theory. One is classical free electron theory, second is quantum free electron theory, and the third one is the last and advanced zone theory or band theory. So the first theory was developed by scientists Drude and Lorentz in 1900. According to this theory, they assume that the metal contains free electrons which are responsible for the electrical conductivity, and electrons obey the laws of classical mechanics. That means the electrons obey Maxwell-Boltzmann distribution statistics. The next, in 1928, Sommerfeld developed another theory that is quantum free electron theory. According to Sommerfeld, the electrons move with a constant potential, and this theory obeys quantum laws. That means the electrons obey Fermi-Dirac statistics. Now in the same year, 1928, scientist Bloch introduced another theory, that is band theory, and according to this theory, free electrons move in a periodic potential provided by the lattice. That means an electron moves in a periodic potential representing the nucleus and the averaged potential of other electrons. So this theory is also called band theory of solids, and it is the latest theory, and it gives a complete informational study of electrons. Now we will start classical free electron theory. So in the classical free electron theory, scientists Drude and Lorentz had assumed some features. They assumed that in metals there are a large number of free electrons moving freely in all possible directions, and electrons move in a straight line between collisions, and velocity changes instantaneously but direction is random. So the electrons are moving in all possible directions, and hence they ignored the electron and electron ions interactions in this classical free electron theory. The next point, in metals, the positive ion cores are at fixed position, and the free electrons move randomly and collide with either positive ion cores or with the other free electrons or with the boundaries, and these collisions are elastic. Therefore, the electric conduction is due to the free electrons only, not the core electrons, because the core electrons are tightly bounded by the nucleus. Now the third point is, they assume that those free electrons behave like gas molecules in a container, obeying the laws of kinetic theory of gases. And in the absence of external electric or magnetic field, the energy is associated, that is 3 by 2 kt, and 3 by 2 kt is, all of you know that the from the equipartition theorem, the 3 by 2 kt is equal to half m VTH square. E is equal to 3 by 2 kt, you know from equipartition theorem for three-dimensional material, and kinetic energy half m VTH square is equal to 3 by 2 kt, where VTH is the thermal velocity and k is the Boltzmann constant. And they assume that the electrons' velocities in a metal, as they are classical particles, they obey Maxwell-Boltzmann distribution of velocities. And the electrons move in a constant potential field, hence the potential energy of the electrons is constant. The seventh point, the last point, is when an electric field is applied to a metal, free electrons are accelerated in the direction opposite to the direction of applied electric field with a velocity that is called drift velocity. Now these are the assumptions they have taken. Now the next part is how the mobile electrons become mobile. That means when we bring Na atoms together to form a sodium metal, the orbitals overlap slightly and the valence electrons become no longer attached to a particular ion. They belong to all. That means a valence electrons, they can move in all possible directions and they belong to the whole crystal, since it can move readily from one ion to its another neighbor atom or neighbor ion and so on. Now, what are the success or advantages or merits of classical free electron theory? So, using this classical free electron theory, we can verify Ohm's law, we can explain electrical and thermal conductivities of metals and the Weidmann-Franz law. So, first we will start Ohm's law. According to the free electron theory, all of you know that because of the random motion of electrons in a free field, the electron motion or resultant velocity is zero. That means no current flows within the metal or conductor. However, when a macroscopic electric field E is applied to a conductor, then a potential difference across its ends is developed. Let's say I current flows through a conductor and R is the resistance. So, all of you know that the volume current density J is equal to current by area of the conductor. And the field strength along the conductor E is equal to minus dV dx, where V is the potential difference, R is the resistance and I is the current. So, all of you know from Ohm's law that V equal to IR. So, I equal to J into A. So, just by using the simple mathematics, we can verify that the J is equal to sigma E, where the resistivity rho is equal to R is equal to rho L by A. So, rho is the resistivity and sigma is the conductivity. So, rho is equal to 1 by sigma. Now, we can prove or we can estimate or evaluate the electrical conductivity sigma using classical free electron theory. So, what is that? The macroscopic electric fields E, when applied in a metal or conductor, then each electron, the electric field pushes each electron with a force, that F is equal to minus small e into capital E. E is the charge of the electron and capital E is the electric field, and it gives the acceleration A is equal to minus E by m into capital E. So, this is the electron's acceleration between the collisions. But during each collision of electron with an ion, the electron's velocity vector randomly changes its direction. Perhaps it continues forwards, perhaps it bounces back, and it can go all new directions and they are equally probable. So, the velocity of an electron is altogether V is equal to V0 plus AT. So, we can write V0 minus small e by m, capital E into t. We just put the a value, acceleration value in this equation, where v0 is the velocity of this electron acquired after its last collision with an ion, and t is the time since that last collision. So averaging this velocity vector over all the electrons in a macroscopic piece of conductor, we can obtain the drip velocity Vd is equal to average of Vd is equal to average of V0 minus A, that means E, small e into capital E by m, and average of time t. So, moreover, since an electron-ion collision, the electron is equally likely to bounce in all possible directions. The average velocity vector right after the last collision is always 0. That means the average of V0 is always 0. And also at any particular moment in time, average over times t that the electrons had since their last collision with an ion, it is the mean time between collisions, that is the average t is called tau, relaxation time. So the Vd, that means the average velocity, is equal to minus E tau by E tau capital E by me. So all of you know that in the absence of macroscopic electric field, the electron gas as a whole stays at rest, no current flows. But whenever macroscopic electric field E is applied, then the electron gas starts drifting with the Vd velocity, drip velocity. Consequently, there is electric current having current density J is equal to minus En drip velocity Vd. So Ne is the free electron density, and you just put here J equal to minus Ene and the drip velocity term, then you will get the J is equal to sigma E. So sigma is equal to N square tau by M. Now that means by using classical free electron theory, we can obtain the electrical conductivity. Now, what is the temperature dependence of electrical conductivity? So, in the classical Drude-Lorentz model, we have found that the relaxation time tau is equal to L by Vt. So, L is the mean free path of an electron and Vt is the thermal average speed of an electron. The mean free path L, what is that? The average distance an electron travels between collisions with the ions, while the thermal average speed of an electron increases with temperature. That means the Vt is proportional to root over 3 kT by m. That means the Vt proportional to root t. So consequently tau proportional to 1 by root t. So the sigma is proportional to 1 by root t and resistivity proportional to root t. So this is only mathematics. However, experimentally proved that the resistivity is linearly proportional to the temperature. So there is some drawback in the classical free electron theory. Now the third point, that is we can verify Weidmann-Franz law using classical free electron theory. So Weidmann-Franz law is the law which relates the thermal conductivity K and the electrical conductivity sigma of a material, which consists of somewhat freely moving electrons in it. So what is thermal conductivity? It is the degree or measure of capacity of a material to conduct heat, and the sigma electrical conductivity, it is the measure of capacity of a material to conduct electricity. So in this law, Weidmann-Franz law, this defines the ratio of the electronic role of the thermal conductivity of a material to the electrical conductivity of a metal is directly relative to the temperature. That means K by sigma proportional to T. So K by sigma is equal to LT. L is the Lorentz number. So from Weidmann-Franz law, we can say that the K by sigma is similar for all the metals, and it is also a function of temperature. So this law is known as Weidmann-Franz law, and we can conclude that the most excellent electrical conductor will be a best thermal conductor. But there are some limitations of Weidmann-Franz law. The value of L is not the same for all the materials. That means the materials, for a specified materials, they have certain K and sigma value. That is why the L value is different for different materials. And it is experimentally verified that this law is not valid for intermediate temperature. This law is only valid for low and high temperature. Now, what are the limitations or drawbacks of classical free electron theory? So all of you know that the electrons are quantum particles, so they follow the Fermi-Dirac statistics. That is why using classical free electron theory, we are unable to explain the electrical conductivity of semiconductors and insulators, and we can't explain the temperature variation of electrical conductivity at low temperature, the concept of specific heat of metals, and the quantum phenomena like photoelectric effect, Compton effect, blackbody radiation. They couldn't be explained by classical free electron theory. And it also fails to explain the temperature dependence of paramagnetic susceptibility and ferromagnetism. So that is all for classical free electron theory.